So today we have a guest from Germany, Stephan Roth. He works at DESI, but also at KTH. Stephan is an expert on functional materials, and he specializes very well in different scattering methods, such as GISAXS and GISAXS. He will tell more about them today to us. And also Stephan is an expert in machine learning. The group of Stephan has some cool articles even from 2010, 2009, the one you sent to me. And we met each other actually at the REC summer school in Estonia last year. So with this very short introduction, I give word to you. Please, you feel free to tell more about you, and we're looking forward to your lecture. Thank you.
Yeah. So first of all, thank you very much, Volodymyr, for giving me the opportunity to present my research work here, and thank you very much for this very nice introduction. And I say hello to all of you and happy to see you and to hear you. And yeah, as Volodymyr said, we met in Estonia in the Röntgen Angstrom School. We had some very nice discussion about what we could do together. And as you have heard, I'm both here at DESI and at KTH in Stockholm. And yeah, we had some discussion what we can do together potentially. And my fields of research are based on the general work of sustainability. And yeah, I'm a physicist by training. I'm actually, as you can see here, in the Department of Fiber and Polymer Technology at KTH in Stockholm. So I'm a chemist by position, but a physicist by training. And as I always say, I work at the interface between physics and chemistry. And with this, I want to start my talk, as I said, with what is usually called sustainability. And the mission of my working group is to develop and fabricate functionalized polymeric materials on biobases. And I've chosen here this nice example. This is not from me, this is actually from literature. You see here a wooden house. You see here cellulose nanofibers. They have integrated a solar cell. And this is one of the first steps when you talk about sustainability. The materials should be renewable and best, of course, on biobases. I look also into processes. Yeah, you want to make processes greener. You want to use the same functionality with less material input. Of course, you look into energy harvesting, like, for example, solar cells or thermoelectrics. We try to avoid what we call the nasty solvents. We try to replace them, for example, with non-halogenated solvents. One part Volodymyr also mentioned is the machine learning, which we are now incorporating into our data analysis. And all in all, this should help in establishing a more resilient society. Yeah, what we are doing here thus is we are looking to applications as thin film electronics, functional materials, solar cells, and we use, as Volodymyr said, heavily X-ray and neutron scattering. Just to give you a glance, when we look into functional devices, we want to see how in real time these functional devices, solar cells, these OLEDs are fabricated, and when they are under functioning, what is happening during their operation. And the typical methods we are using is spray deposition. This is compatible with roll-to-roll coating, like 20 meters per minute. You can do advanced 3D coating. Yeah, I always say, yeah, you can spray coat a car, but you cannot spin coat a car. We are looking into additive manufacturing, like flexible electronics, and a big part of my work is physical vapor deposition, where we look into high-density cluster layers and structural colors. And when Volodymyr and me discussed on the invitation here, we decided that I will put the main focus on physical vapor deposition, and this is what I actually did in agreement with Volodymyr. Volodymyr, I think you said to me I have 1 hour for the talk.
Yeah, that's correct, but you are not limited. You yourself decided that you want 1 hour. If you
I
need
don't
more,
want to annoy you. We can do as much as you
no,
want, as long as you want. Yeah,
you
no
can make it
problem.
longer. But also important question I forgot to ask. Do you mind questions along the lecture? Or you would rather have all the questions in the end?
Maybe it's better at the end,
Okay.
because then you have seen everything. We can take our time at the end. I can always jump back.
Okay.
We can maybe after the first part make a question round, immediate question round, and I give the second part, and we can then have general questions at the end of the talk.
Yeah,
if you want.
good.
Okay,
Good.
great. So, and again, here to pinpoint it, we want to elucidate the nanostructure function relationship via scattering methods for all of these 3 main methods. To give you a detailed example, solar cells, energy harvesting. Of course, one big issue is the scalability. You don't want 1 centimeter squared, you want meter squared. And on this meter squared, especially with these flexible solar cells, these polymer solar cells, you want to establish a certain nanostructure. Typically, the active layer here are polymers, semiconductive polymers with this kind of phase-separated structure. The solar light creates an exciton. The exciton diffuses about 20 nanometers before it recombines to the interface. The charges are separated and then go to the corresponding electrodes. And the mechanism of establishing this photoactive layer, the electrodes and their combination, this is the typical area of research we have. And just to give you an example, when you fabricate a solar cell, we want to correlate every step with a nanostructure. And typically, these organic solar cells have 7 layers, meaning 7 process steps, not 7 different technologies, but typically you have spin or spray coating, slot die coating for the polymer layer. You can have liquid deposition for the silver nanowire layer. I will show an example. You can have physical vapor deposition for the electrodes or for the oxide layer. And what you first do, of course, is you use an AFM to look into the structure, but it's always the topmost layer you see. And this is why in that example, 11 years ago, we used on each deposition step grazing incidence small angle X-ray scattering to check the length scales and how these length scales change. And you see here, indeed, when you deposit another layer on top of an underlying layer, these length scales change. And keeping in mind that we want to have a majority of the length scales in the active layer in this exciton dissociation diffusion length, yeah, you see this can become rather complicated, and therefore it's very important to look at the influence of processes on the nanostructure. Yeah, and here's the outline of my talk. I would like to start with a short explanation what grazing incidence scattering is. I might always say X-rays, but it's basically the same for neutrons. And then we look into sputter deposition for functionalizing materials. And I have decided on, for examples, biosensors, electrode formation, how we can use diblock copolymer materials as advanced templates, and then look into a new method which is called high power impulse magnetron sputtering, HIPIMS. And in the second part of my talk, we go more to the liquid methods. We look into hybrid materials for solar cells. So these are basically electrodes. And now we go in the end to the full solar cell. I will show you how we can include wood-based materials as the nanoporous template, and then how we can fill this template with the material of our choice, and that we can even deposit very easily electrodes. And then I show finally some applications. So let's start. When you do grazing incidence scattering, your sample is typically lying nearly flat and the X-ray beam is impinging under a low angle, 0.4 degrees around with X-ray energies in the range of 10 to 13 keV onto the sample. And then the X-ray beam can undergo direct scattering. This is the Born approximation, or it can be reflected scattered, or scattered reflected, or reflection scattering reflection. And all these four terms need to be taken into account when you calculate the scattering cross-section or the final intensity. And you see here, this is the particle form factor, which we know from classical Born approximation, and this is then weighted by the Fresnel reflection coefficient. And you have to take then into account the changing of the vector direction. And then, like in normal SAXS and WAXS, you can position your sample or your detector close to the sample, like 10 to 30 centimeters or farther away, 1 meter, 2 meter, 10 meters, 13 meters. And then we distinguish again between grazing incidence wide angle X-ray scattering and grazing incidence small angle X-ray scattering. And when we start with the GISAXS, this is this image here. This is like classical Bragg scattering or diffraction. You see the crystalline size and orientation, and this is highlighted here. If you have a layer by layer growth like this, very conformal, you see here Bragg dots, where the distance of the layers corresponds to 2 pi over d. You can imagine this as atomic layers, for example. When you have a certain mosaicity, like in this case orthogonally, you have Bragg spots in this and in this direction. When you have a slight tilting, you get arcs, and when you have more powder-like structure, you get these powder rings. Here's the full scattering vector, vector Q, taking into account that we have an incident angle, we have a finite exit angle, and an off-detector angle leading to diffuse scattering. And of course, the size we measure in real space is inversely proportional to the size we see in reciprocal space. Size is proportional to 1 over Q. And in order to fully analyze this, we have to map our two-dimensional flat detector onto the Ewald sphere, which gives rise to this pattern. And you see here an inaccessible range, which means that in GISAXS, a certain range in Q space is not accessible due to the symmetry breaking of the sample. Good. So this was the GISAXS, and now you see how we analyze this. We can make cuts along this, these peaks here. Yeah, with this we can, in this azimuthal cut, we can find out orientations, as I've showed on the slide beforehand. When we make this pseudo-XRD cut, we get here peaks which correspond to atomic layer, to atomic distances. And then we can, via the Debye-Scherrer equation, deduce the crystallite size, where the crystallite size is then inversely proportional to the width of such a Bragg peak. This allows us really to get out the interatomic distances or intermolecular distances, the sizes, and the orientation of the crystallites. And we have developed together with TU Munich a program for this. Yeah, when we move now our detector farther away, we are looking in the small angle regime, and this is a typical scattering pattern. These are just 100 nanometer colloids, polystyrene sprayed on a silicon wafer, and you see a wealth of structures again. You see here the dots, which stem from the more or less regular arrangement of these spherical colloids. You see here the sample horizon. You see here resonant diffuse scattering. You see here strong Bragg rods, indicating that we have really a preferred nearest neighbor distance. And in order to analyze it, we make so-called cuts. We make a horizontal and vertical cut. And in the horizontal cut, if you follow this, you see here a strong peak in the middle. This is called the Yoneda peak. I will come into it in a minute. And you see here this maxima. And this is like Bragg scattering. It's a pseudo-Bragg peak. The position of this Bragg peak is inversely proportional to the real space distance. And then we can get out from this cut features in the sample plane like nanoparticle radii and distances. If we then look in the vertical direction, we find out that we have here again maxima and minima. These are the maxima and minima, the fringes stemming from the height of nanoparticles of layers. And we see here an interference phenomenon, which is called the Unida peak, and its position is characteristic for the material present. It's the angle of total reflection, keeping in mind that the refractive index for materials in the X-ray regime is smaller than 1. So vacuum has 1 and each material smaller than 1. This means if I shine my X-rays under a very low angle onto the surface, they get totally reflected, and you measure this position on a detector and you can deduce the density of your materials present in the sample. And all this allows you then to get a full three-dimensional morphology picture of the thin film. To analyze the GISAXS, to show you directly here, we are able to simulate the scattering pattern. This is again 100 nanometer polystyrene colloid sprayed on a surface with slightly different parameters than shown beforehand. And if we look here into this cut again, this is the red line, we see again the maxima and minima. We can make what is called an effective interface approximation, where we assume a certain structure and size and just calculate via particle form factor and structure factor the scattering pattern. Or we make a full two-scale, two-dimensional simulation, and this is the green line. They are just shifted for clarity. You see that we can quite well reproduce all the features of the experimental data, and in this specific case, we could even tell you how many layers are on top of each other of the colloids. Yeah, this is, so to say, the nice scattering pattern. Typically, scattering pattern look like this. They look more featureless because other examples like cellulose or other wood-based materials, they give a more disordered structure. You see here the typical scattering patterns, and here again the one-dimensional cuts. And then we have to apply a more advanced modeling where we include a resolution function on our sample, and we include our different components as form factors. And by incoherently adding all the three components of the different structures, so structure factor times form factor, and you add it, we can quite well reproduce the curve, and we find these structures in the experimental data. So this shows you the method of grazing incidence, that we can really go from the molecular level to the nanoscale or mesoscale level in full detail with all structures, and we are able to quantify all structures present. And now let's start with sputter deposition for functionalizing our materials. So this is the setup we are typically using. This is at the Beamline PO3 in Hamburg. This is a photo which my PhD student Yusuf Bulut made. You see here a very big sputter chamber. Here is the synchrotron beam coming. We have here one detector at the wide angle position, GISAXS, and the second detector far away between 2 and 4 meters for the GISAXS part. Yeah, you see here, this is a typical scattering pattern of the metal on a polymer film. You see here these powder rings from the different reflections of the metal clusters, while here you see the metal layer growth, the nanostructure of the nanocluster layer. And very important is we do this in situ and at the same time. So we are depositing and measuring at the same time both the crystalline reflections and the small angle part. And just to remind you, this is how we picture it. We put a very big sputter chamber into the beamline. So sputter chamber, it's a vacuum chamber. We fill argon in, and we ionize the argon. And with this, we kick out target atoms from a target. This can be gold, silver, aluminum. These are the three metals I'm focusing on in my talk. And then these atoms fall on the substrate. They diffuse on the substrate and create nanoclusters. And while these nanoclusters are growing, we observe their growth with grazing incidence small and wide angle X-ray scattering. And here we have developed an analysis method. When you see a side peak, we can relate the side peak again to the position. This is like a Bragg peak. Peak means 2 pi over d, and d is the distance. When we look in vertical direction, we see again here the Unida peak, in that case of gold. This is a specular reflected peak. We don't need it, we block it in order not to harm the detector. And then you again see here fringes, which tell us the thickness delta of the deposited, in that case, gold layer. And we have developed what we call a geometrical model. We know during sputter deposition, clusters occur on the surface. The distance of the clusters, d, gives rise to this peak here. When we now know how much material is on this is this delta, and assume a hemispherical cluster shape, we can calculate the radius of our nanoparticles only by the position of this peak and by knowing how much material is on. And this allows us during the deposition to follow the nanostructural growth of the cluster. And this is just one model. We show here the typical nucleation regime, the diffusion regime, and then the percolated regime, and finally the regime where the clusters only grow in height after percolation. This we can deduce with this simple model. And on this slide here, just to show you on the left side, this is a video from the different GISAXS images, just one after the other. This is slow GISAXS experiment, 10 frames per second. You see here the evolution of the nanostructure. If you look closely, let's wait a second time. Here you see a peak going in. So when this peak moves in, this is in reciprocal space. Of course, this means that the nanostructures are growing. At the same time, you see here that maxima come from the top. This means that the nanostructures are growing in height. Perfect. So we can deduce our growth, in that case, of gold clusters on a polystyrene film up to the percolated regime. And here you see a molecular dynamics simulation, which have done our colleagues in Kiel. The group of Bonitz has done this. They really put atoms on the surface and let them diffuse with the diffusion coefficients we deduce from our GISAXS experiment. They come together and they build clusters. And you see that this shape, when you calculate the distances, this resembles what we deduce here from our model. However, they percolate at 3.45 nanometer, while we percolate at around 6 nanometer deposited gold thickness. So there's still some work to do on the molecular dynamics part. But all in all, this looks very good. We can reproduce all the different stages. If you look closely to this video here, you see that here something is moving. Actually, this is the sample. This is the direct beam, and the sample is moving through the beam. When we go to third generation sources, the intensity is so high, if we would stay on one position, we would burn the sample and effectively alter via radical formation the growth of the clusters. This is why we move the sample through the beam stays constant, you cannot move the synchrotron, and by this we are able to distribute the dose on the sample surface and really tell you that this is the real cluster growth unaffected by the X-rays. And to show this here in more detail, first of all, you see here, this is silver on silicon. You see here SEM images of different deposited silver thicknesses, and in black you see a histogram, and in red you see the analysis via GISAXS, and you see that we can quite well redistribute with our GISAXS analysis the histogram provided by SEM. Secondly, to really prove you that we do not alter the morphology, of course, you take the sample out and you make an experiment without the beam, but we also scanned our sample through the beam after deposition. And you see here, this was our, between -1 and 1 was our scan area during the in situ experiment. And when you scan over the whole sample, -2 millimeter to +2 millimeter or over a larger range, you don't see any change, meaning that the structures where the beam was not present and the structures where the beam was present are the same. So we are sure that we don't have any influence of the X-ray beam on our sample. And this is the advantage of then using micro and nano beams. We avoid the alteration of sample morphology. We use short exposure times, we use stroboscopic measurements, sample scanning, and at the same time you can check if the people who spin coated, in that case the sample made a good job, and if the sample is homogeneous. So this has only advantages. So staying with gold on silicon, this is the first functional material we use. Silver, like other metals, has a plasmonic resonance. When you put two silver clusters into close contact or very close to each other, and you put a small molecule between these clusters and you shine a laser on, you can excite the Raman vibrations of this molecule, and these Raman vibrations are enhanced by the electromagnetic field created by the plasmon resonances of these small nanoclusters. And this method is called surface-enhanced Raman scattering. So you make a thin metal layer, you put a droplet with your molecule on, and you can detect trace molecules. And with this experiment here, it's a straightforward experiment. We make an in situ experiment from 0 to 10 nanometer deposited gold on silicon. We know that the silver nanoclusters grow in hemispherical structure. We know their structure from the island region up to the percolated region. This is here on top shown, 2.8 nanometer, 4.2 until 8.4 nanometer deposited thickness of silver. You see here the side maximum moving in, meaning that the clusters grow. You see here maximum coming from top and moving in, meaning that the clusters grow also in height. In the bottom, you see the simulations, and you see here by the arrows, we can quite well reproduce the Unida peak, the side peak also in its extension, and we can reproduce the height maxima too. This is just this hemispherical model. Now, you can produce ex situ these samples, and you can make this surface-enhanced Raman scattering experiment, and you can check what is the sensitivity. So here we used one of the standards, I think it was R6G, rhodamine 6G, and then you measure the Raman signal as a function of the deposited thicknesses. So you make 10 samples with different thickness, you put your analyte on, and you find out that around a deposited silver thickness of 5.6 nanometers, you have a strong increase in the SER signal. And the question was, why? And the reason is here in the structure. If you imagine this triangular structure of hemispheres, the distance d gives rise to this side peak. We have between the clusters a void size, delta. And we can calculate this void size. It's basically distance minus 2 times the radius. And you see that this void size decreases. So you can say, well, here clusters are far apart, and here the clusters touch each other. Then the clusters touch each other, you cannot put a molecule in. It's exactly what you see. First, the cluster surfaces become closer to each other. You have an increase of the electromagnetic field up to 0.9 nanometer, and then again you have a decrease in hotspot density because the clusters grow together. And you have an optimum around 0.9 nanometer of void size, and this around 5.6 nanometer, fitting perfectly what you measure here. So this was a very nice example to understand the functionality on the sensor based purely on the structure. Good. Now let's go to electrode formation and diffusion layers. So we start with a model system, gold on polystyrene on silicon oxide, spin coated. We do the same experiment as I've shown you beforehand, in situ deposition of gold on polystyrene, in situ GISAXS at the beamline. Here are shown selected GISAXS images, and here the corresponding simulations. And here you see already that we can even go to very fine detail. When you let grow gold on polystyrene, it's no longer hemispherical, but in the beginning it's nearly spherical, then it becomes hemispherical at one point, and then the clusters become flatter and flatter, and in the end they touch each other and grow in height. And this change here, when you produce a gradient, you see also here from pure polystyrene to the very thick gold layer, this is 8 nanometers of gold, you see a strong color change indicating the change of the cluster size and distance. And this is what we wanted to do. We wanted to correlate here the nanocluster layer morphology with its optical spectra. And first of all, what we can do is we can tell you all the details about the nanoclusters. Here you see the deposited thickness. Here you see the 2R/D ratio, meaning diameter divided by distance. Yeah, in the beginning, you have many small clusters far apart. 2R/D, very small. This increases because the clusters grow and grow and grow. You follow the blue curve. At one point, the clusters which could move on the surface are too heavy, and they stay in their position, and they just attract and trap all the other atoms coming in. So basically means the distance stays constant, and they grow a little bit in size by eating. No, sorry, the distance grows, and they grow some kind of Vollmer-Weber growth. Sorry for that. That the big clusters eat up the small mobile clusters, and therefore we have this dip here because the distance increases by eating up small clusters, so to say. And when we continue with the deposition of gold, the clusters grow and touch each other. And when they touch each other, we have a percolated layer. So by simply analyzing the 2R/D ratio, we can tell you when this layer should become electrically conductive. We can also give you the cluster density here in full detail, and we can give you the cluster shape. So this is the phi angle, meaning phi equals 180 is a full sphere, 90 is a hemisphere, and 60 or below 80 is one of these capped spheres. So we can follow really the size and the shape of the clusters in all detail. We can also deduce by our measurements diffusion coefficients of gold on a surface, which is viable input for the molecular dynamics. We can, of course, compare to SEM images, which fits very good. And we can compare to optical measurements. And then you see, for example, that for very low depositions here, 0 to 2 nanometer, you have an anti-reflective coating due to the existing plasmon resonance. And only when you continue above these 2 nanometers, when more and more gold comes on, the reflectance goes up and up and up, as you would typically expect for a gold layer. And this can, in this region here, can be used for Serre effects. Good. Now, as we talk about gold on a polymer layer, when I give this lecture on GISAXS for students, I always ask them to draw an electrode. Yeah, and then you have it always, you have here a layer which you want to contact and an electrode, and they always draw it with a sharp interface. When you look in detail, it's not a sharp interface. So I show you here an example where we deposit gold on a semiconducting polymer. This is for solar cells to create an electrode. Again, here you see the experimental data, the simulated data, and we can go into all details into the growth laws of the nanoclusters with distance, radius, and height as a function of thickness. But what is more important, when we made an X-ray reflectivity measurement, we found an enrichment layer between gold, top layer, and polymer sublayer. And this was the first time actually this was found for solar cells. And this explains somehow that the electrode worked because you have a diffusion layer. So the band gaps go smoothly from the semiconducting polymer to the gold electrode and thereby enhance the charge carrier extraction. And what we asked at that time, this was purely ex situ, you see this is 2009, can we see maybe how this gold layer, this enrichment layer really grows? And this is what we did actually then. You see here quite some time later, because this took into account the advances in synchrotron radiation from second to third generation and advances also in data analysis. So what we did here, we used a very high sputter rate, 1.5 nanometer per second. The other experiments I have shown you up to then were 0.1 nanometer per second, 0.2 and so on. And when we told this to industry, they said, you're much too slow. So we said, okay, we can do better. And we managed 1.5 nanometer per second, which is still the record in deposition in situ deposition with GISAXS. We again sputter deposit gold on polystyrene thin film. This is again typically 100 nanometer. And in 1 second, you go from, from this image, excuse me, I need to drink something. Yeah, here to this image. Yeah, so from a polystyrene layer to a cluster layer. And we take 2000 frames per second. Yeah, this means when the whole experiment is 3 seconds, you get 6000 images. Yeah, in 3 to 10 seconds. This means that if you run this continuously, you can imagine how many gigabytes you would produce. And what we then typically do is we make these maps. This is the time or deposited gold thickness. This is the exit angle, alpha E, and color-coded is the intensity. So we plot here the vertical cuts. And then you see here fringes, and these fringes move. Remember what I said? These fringes have to do with the layer thickness, and the maxima have to do with the Yoneda peak. And the Yoneda peak is proportional to the square root of the density. So something is happening here where the density changes. And actually, we look again at these density changes, and what we find actually is first, we make a normal analysis of the clusters. Yeah, we see here how many gold atoms are in a cluster. We can detect up to 2 atoms, down from 2 atoms up to 10,000 of atoms per cluster. We follow the cluster density, and we follow the aspect ratio. And for example, we found here out that if you put only 2 gold atoms on top of each other, they are really on top. They are like a molecule standing like this, and only with more clusters incoming, gold atoms incoming, they are flattening. But what is more important, we were able, via these fringes here, to analyze the polystyrene layer thickness and its density. And what we saw is these 2 lines here. See at the time, these are the first roughly 3 nanometers. This is not a solid line, but these are individual measurement points. But because we have 2000 frames per second or more than 2000 frames per second, it looks like a solid line. What we did use here is actually the remaining undisturbed polystyrene layer thickness. And you see it's decreasing with time. So we see that we have a diffusion layer where gold diffuses in with time from 0 nanometer to roughly 5 nanometer. And at the same time, we can tell you the loading of this diffusion layer. Yeah, and it's only between 0 and 1.4% of gold atoms which diffuse into a 5 nanometer layer. So in the next step, I would like to make this a little bit more complicated. We go away from our pure layers and we use diblock copolymer materials. So these materials are 2 polymers which are covalently bound. We spin coat our layers. Typically they have 20 nanometer to 100 nanometer thickness. We put our sputter chamber into the beamline. We deposit our metal. We measure GISAXS. We can measure ex-situ XPS and SEM, and we can measure the conductivity. And this becomes now important that we are really able to deduce, and I will prove it to you, the electrical conductivity onset in our systems. And why we are doing this is that we want to understand selective wetting and influence on optoelectronic properties. Why selective wetting? When you ask what is the interaction between a metal and a polymer, the answer is this depends. If you take gold, it reacts differently with polystyrene or with PMMA, polymethyl methacrylate. If you use silver, again, it's completely different, and so on. Especially when you then look into these all fancy polymers which you use for solar cells, you actually have to experimentally deduce this interaction. This is what we are doing here, this interaction between the different metals. And as metals, as already indicated, I use gold, silver, and aluminum, because then I have a broad tunability of the plasmon resonance, and I can avoid or dedicatedly introduce oxide layers. So, to start with is solar cells, we use conjugated diblock copolymers. They have a donor and acceptor part, or they have one semiconducting part and one coil part, And by this, you can make nicely solar cells with a certain nanomorphology out of it. Yeah, they are somehow difficult to nanostructure. You need to tune the right solvent. And especially what you can do is you can use these rod coil polymers with one of the conjugated polymers, P3HT, for example, and an amorphous PMMA block. And you can remove the amorphous PMMA block quite easily. And then here you have this standing lamella of the P3HT, and you can backfill this then, for example, with buckyballs or other non-fullerene acceptors. And our question is how does the electrode grow on this? And what's the cheapest electrode you can do? It's aluminum. Gold expensive, silver semi-expensive, but heavily used by semiconductor industry, so we use gold. We did this indeed in the past for looking into electrodes for LEDs. We deposited aluminum on aluminum quinolate, and we could follow in all details the stages of growth of the aluminum layer. And again, we also found here an aluminum intermixing layer, which we have explained in the last part with gold. When you have these diblock copolymers, the first thing you do is you have this nice structure, they are phase separated, and you deposit your metal, in that case aluminum. And you make an AFM image. We have 2 nanometer, 4 nanometer, 6 and 8 nanometer, 1, 2, 4 and 8 nanometer of aluminum. And you see here when there is no aluminum on, you have this pink line. Then you start to deposit aluminum on, and you see that basically the aluminum reproduces the roughness of your substrate, and it goes even up to 2 nanometers, and from 4 nanometers you see that this roughness reproduction goes down and down until 8 nanometer. So actually what is happening is that aluminum goes selectively to one part of the diblock copolymer. And if you look at the distance of peak to valley, you can plot this here, and you see that this peak to value first increases, aluminum selectively grows on one block, and then it goes down again, because then the aluminum goes also to the other block. And then you have the growth of aluminum, and these two growth modes, these two growths touch each other, and you finally have a full aluminum layer. Good. This is with AFM, and you can confirm this. Then with XPCS, you can look at the chemical interaction. You will see in all spectra that actually aluminum interacts with the carbon molecules of the polymer. Aluminum interacts with the oxygen, nothing new. And when you look into the aluminum signal, you see a strong metallic aluminum peak, meaning that we have really aluminum, pure aluminum growing. And this is then what you see also in the GISAXS signal. Good. We have a nanostructure template. We start to see how the aluminum interacts with the different parts of the diblock copolymer, and we can create a full electrode. And then if we look with AFM in more detail, you can really see here, when you put a little aluminum on, you see these are P3HT domains. They always have a worm-like structure. You see here clusters growing on these worms. You see it here even better at 2 nanometer. They become very large at 4 nanometer, and at 8 nanometer, you lose this worm-like structure, meaning that now the aluminum indistinctively grows on both of the domains of the diblock copolymer. And this is also what we see in situ. We start here with these images. You see here for the diblock peak, for the individual P3HT layer, and for the polymethyl metacrylate, you see the growth of aluminum. You see this looks completely different. Now you see here aluminum on PMMA gives here only very small signal, and here a broad side signal, and here you see a very nice height growth. And on the diblock copolymer, you see here a peak which stems from the lamellar structure of the diblock copolymers and the cluster peak. And this cluster peak resembles very much the peak you find on the P3HT, confirming what we saw in the AFM, that the aluminum grows preferentially on the P3HT. And from the overall shape, we can find out that the clusters really grow in hemispheres. You make an AFM image. You see these clusters here, they look round. We know from the GISAXS analysis they are indeed hemispheres. and you see here clusters of clusters, which again make up here a second cluster peak. Good. We can again make a map here. This is the deposited aluminum layer. This is QY, so on horizontal cut and intensity coded. You see here the structure peak of the polymer, and you see here the side peak moving in. These are the aluminum nanoclusters growing on the surface during deposition. And when you follow here, actually, this diblock copolymer peak, you see first an increase in its signal. Well, the polymer doesn't change, but what changes is that the aluminum grows selectively on one block. So you increase the electron density difference between the two blocks of the diblock copolymer. It grows on P3HT and not on PMMA. So I have here something like polymer plus aluminum versus polymer, and it increases. And then suddenly this intensity starts to decrease, because then I fill up the other part, the PMMA. The PMMA is saturated, and I grow on the PMMA, and hence the scattering contrast goes down, and then we have an overall increase in the signal because we have aluminum growing on top and the X-ray scatter on the aluminum. And this is what we then can find out. We have first a nucleation and embedding formation of the merged clusters on P3HT. In phase 2, we have selection diffusion mediated growth. The clusters coalesce and grow on this P3HT worm-like structures. And then at one point, also we have growth on the PMMA layer. And finally, we have a percolated layer. Good. We can in all details find out distance and radius. We have a reduced diffusion of aluminum on the copolymer. We see a linear growth, not like we see a nonlinear growth for gold on polystyrene. We see an embedding. And now an important point is we can deduce for every of our materials the percolation threshold. We plot here simply 2 times the radius divided by this. And when it's 1, the clusters touch each other, and we should measure electrical conductivity. And you see here that P3HT has a quite early percolation threshold. Yeah, if you grow on a reduced dimension structure like this worm-like structures, the clusters grow into each other very fast. PMMA is a just flat film, and it grows later, and the diblock copolymer has some hindered structures due to its nanostructure, and therefore the percolation becomes later. Okay, so we can define this in every detail. Then we can look into the optical response. Now we look at the specular reflectance. We see 2 minima called lambda 1 and lambda 2. One stays constant, the other one shifts. It shifts with deposition, and therefore this is induced by the plasmon resonance, and we can easily correlate the spectral reflectivity with the deposited aluminum thickness. Again, we see an anti-reflective behavior for small deposit thickness, and we see that this side maximum plasmon resonance shifts with deposited amount of aluminum. What we also see from the simulations, we see a percolation around 6 nanometer, and here we have indicated this here at 6 nanometer, all of our clusters are percolated. Good, nice. This leads us to the point that we can establish a growth model. This is one of the decisive advantages then of GISAXS, that we can find out all these growth models. We have these nanostructures. Here's the side view. Here's the top view of our diblock copolymer film. We have this aluminum nanostructures growing on this worm-like P3HT structures. They first grow together on the P3HT, and then they start to grow together on the PMMA. And in the end, we have this nice fully percolated electrode. Good. We can change now to a slightly different system. We use silver on polystyrene block PMMA polymer. And just here, when we go through, keep in mind that PMMA, polymethyl methacrylate, has oxygen. And again, we do the same experiment. We spin coat a diblock copolymer film and the individual components. We make AFM SEM, we make GISAXS, and already from only 1 nanometer of deposited silver, you see strong changes in the SEM, AFM, and also in the GISAXS. You see smaller clusters on PMMA, larger clusters on PS. And if you do FTIR, you see that the CO2 stretching in the PMMA is reduced, meaning that the silver undergoes a bonding with the oxygen in the PMMA and thereby shadows this CO stretching vibrations, indicating that really the growth modes are completely different on PMMA and PS. And again, you see the same here. The bright parts, the bright lines here are polystyrene, the dark lines PMMA, and you see that these clusters, silver clusters, really selectively grow on top of the polystyrene. This is what we expect also due to FTIR. Good. We can do the same. We can make the cut here. We can look at the structures, and we see again, confirming with GISAXS, we see an increase of the diblock copolymer signal because the silver grows on the PS. Thereby, we have an increased density difference between one domain, PS plus silver, and PMMA. Then we have a reduction again because the silver starts to grow also on top of the PMMA, and then it grows together and grows and grows and grows, and this is the typical metallic reflectivity. We can then deduce all the sizes. We can again look into 2R over D, and this is now very important. You see here these different vertical lines. This is what we deduce from our structural model as the projected percolation threshold, and we measure this also. And the nice thing is, maybe I go through this a little bit faster, is this here. We can give you for all sputter rates, for all thickness, a nanostructure, and we can compare our percolation threshold from GISAXS with what we measure. And this is what you see, light to gray. This is GISAXS, this is measured. And you see that our onset of electrical conductivity determined by GISAXS as well as by real measurements in the lab correspond. So we are able to tailor the metal layer electrode and determine the minimum layer thickness for conductivity, and we can even tune our absorption by small metal layers and thereby increase the efficiency of solar cells. Okay, this would be nearly the first part of my talk. I go just very shortly. Let me explain you HIPIMS. This is high power impulse magnetron sputtering. So you put in a short time a lot of metal on a surface, and we are able really for different polymers to look into the growth. And one important point is when we compare this HIPIMS to DC, what we see is that this HIPIMS structure really gives many small clusters in smaller distance. Smaller clusters in smaller distance means higher cluster density, so a more compact layer compared to DC. We can look also into the crystallite structure. We can look into the adhesion. And what I want to show here is when you are able to create compact layers, this is titanium dioxide, which we sputter, you can use this as a very compact blocking layer to reduce defects. That's exactly what we did here. We are able, by sputter depositing a 10 nanometer titanium dioxide layer with this HIPIMS, and we get a compact layer, and we are able to increase our photovoltaic efficiency, in that case of perovskite solar cells. Yeah, with this, I would be at the end of my first talk. You see, I have enough material to discuss, and I suggest, as in the beginning, that we make here a short question and answer round concerning the first part, if it's fine with you, Volodymyr.
Yeah, it's fine, and thank you. It's very packed. Like there are many things here, especially for people who are not very familiar with the methods and with the specifics. Because I'm talking about myself. I'm not a specialist in polymers and in scattering methods, as you know, as we discussed before.
Yep.
But at least I know some background about it already. So I'm not sure how it is for everyone in the audience. So does anyone have anything to ask right now, or I can start
Does
with
anyone
some...
dare to ask? You should ask.
There are plenty of
Please
people.
go. Yeah, please go ahead.
I'll just ask some simple and probably silly questions. About GISAXS at the beginning, you said that you can model it as well.
Yeah.
Do I understand correctly that the modeling is essentially like just ray tracing of sorts? and then what's the physics of
Yeah.
modeling? Like, because again, not my method, so I'm just curious.
No problem. So what we do is we assume a certain real space model. So we put real structures on the surface. Yeah, you say this is a hemisphere, this is a full sphere. It can be more than one layer. I have a substrate or maybe an intermediate layer. And then I simulate these scattering processes. Here, it's not really ray tracing, but I know from Born scattering, this is beam in, beam out, and I scatter here at the scattering center. This gives me the form factor scattering or the Born approximation, what you know from transmission scattering. And then with the second coefficient, I weight this second term 2 with the Fresnel reflection coefficient, because as I have here a substrate, the X-rays undergo reflection and then scatter. And then I modify here this component Q in Z with the appropriate directions of incoming and outcoming vector, and I recalculate this contribution of my form factor. Yeah? The form factor is basically the Fourier transform of the density distribution of a material on the surface. And the same I do here. I go with this form factor here. I calculate the vector difference, and then I scatter and I calculate this contribution weighted by this Fresnel reflection term, and here with this two-order reflection similarly. And then I add them coherently and I calculate the intensity. So it's a kind of ray tracing, but not really ray tracing as you know from typical other scattering programs. Yes?
Yeah, I see. And these parameters you probably take empirically for different materials, right?
Okay. We have to take into account here the refractive index of the materials, which is tabulated. And here you have the choice. You can choose distance, radius, height of the nanoparticles and their shape. And there are certain selection rules of how to select the shape. If you look into this part here, for example, this is a very good example. I just told they are hemispheres. You have to look into the position of this maximum in the overall shape of the GISAXS pattern of the intensity, like this triangular shape, to really understand the morphology of your layer of your nanoclusters. If they can grow flat like cylinders or in hemispheres. And this is what we did then in the next part here. Yeah, you see here the changes in the GISAXS pattern, and we assumed a different shape. And this shape then you can optimize and you can really fit this to the scattering pattern. Yeah, based on features like the position of the side maximum here, this structure here, and this structure here close to the middle of the detector.
Yeah, I see, but I understood. Thank you. But like extra question to that, do I understand correctly that if you don't know what you have put into the chamber, like you have no information at all, and then you just start slowly sputtering, you won't be able to guess unless you know that there are like 3 different options. Then you can deduct from that.
Okay. We had this in the past. I can deduce from this position here, from the peaks here, I can even deduce the material. Yeah? So even without telling me, I find out which material is on the surface. Yeah? This is the UNEDA peak. Its position depends on the square root of the density.
Yeah.
So even if you won't tell me, I can figure it out. Then we, of course, I mean, you should know what you put into the sputter chamber. Yeah, of course you can exchange cables. This happened all in the past. Yeah, don't worry.
It's a hypothetical question.
Yeah, at 4 a.m. in the morning, cables can be exchanged, but it doesn't matter. You can easily find it out. And then you see the side peak here, and the side peak gives you the distance. So I know the distance of my particles, and then via this formula here, which I gave, which is a purely geometric formula, we just assume that the deposited amount is distributed into these three clusters, you can deduce the radius under the assumption that they are hemispheres. If they are spheres or cylinders, this factor here changes. Yeah, but this is then one of our points of our key features. Honestly, let me just jump a little bit here. Where is it? When we look into this here, into the percolation pressure, what we always do is we measure the electrical conductivity or the onset of electrical conductivity. Then we calculate this 2R over D value. And if this is 1, we expect electrical conductivity. And if it's later or earlier than what we measure with an with a voltmeter, we know that the clusters are either more cylindrical or more flat. So we need to apply a correction factor. This is typically the case for not so noble metals like copper. They grow in completely different structures, but we can find this out too. So we can, once you know the structure, you can predict every physical parameter you need for electrodes. If you don't know the structure, you need at least one additional experiment to give you a derived value. And by this, you can deduce again the structure, the shape of your nanoparticles.
I see. Thank you. There are actually some questions from the audience.
Yeah.
So I'll switch
Please
to
go
those
ahead.
for now. Alexander, please. Alexander Tomchuk.
Yeah, thank you very much for the opportunity to actually ask some questions. I have two brief ones. You showed the perfect description of the theory behind actually the data fitting, but in practice, what you typically use? I've seen just GISAXS program on one of your slides.
Yeah.
Maybe you work with Born Again or something like, just to give a younger audience a guess.
Yes.
Which program you should play with.
Okay, GISAXS is, I would say, the classic program. It is really, as it said, island GISAXS. You have cluster layer, one spacer layer, and a substrate. This is the reference program developed by Remy Lassari, and we also use it today. Here for all metal on polymer, hybrid materials, I think it's fully sufficient. However, if you have more complex structures, like you would have multi-layers, or even you have a diblock copolymer layer where you have lamella like this, and you have here one cluster layer and a next cluster layer on top, then I would use Born Again, because the structure you can put into is much more complex. And we also use Born Again. But there's one thing with Born Again, it's still under development. The GISAXS program has included the Niveau-Cross approximations that I always explain it like this. If you have two clusters which touch each other, yeah, and you would measure an electrical conductivity, do you see two clusters, or are these two clusters actually one big cluster? Yeah, exactly. So for the electron wave function, if I don't have a grain boundary, it's one cluster. For the simulation in Born Again, I simulate two clusters. In GISAXS, I'm able to take into account that the electron wave function extends over the whole cluster. And this again has differences in the scattering pattern. We see this. Yeah? So, as I said, it depends on what you want to do. As we use for colloidal layers, we use Born Again. And for metal on polymer, we use here GISAXS.
Yeah, thanks. And maybe just one more brief one. Initially, you told about the possibility to use some neutrons in your projects, but all kinetics behind it's typically just a few seconds. Is neutron scattering still useful for you?
Yes. This would be the next part. Yeah. We can skip a lot from the next part depending on you. I have no problems with this. I made it a little bit too long. I apologize for this. Typically for these so we proposed already to include a sputter chamber into a neutron beam line. We proposed already. But then we would do what is called self-sputtering. You deposit a layer and you measure for 1 hour. You deposit the next layer, you measure for 1 hour. You have to make sure that the cluster layer or the layer doesn't grow in that or change in that time, so to say, between two depositions. Here we really do it in situ with X-rays during. Neutrons we use more for our biomaterials when we look into polymers. There are different polymers like cellulose and P.PSS, where we look into the different structures of these polymers, for example, during humidification. Then we know that we can measure for 3 hours per sample without any problem. Yeah. So with neutrons, you are completely right. We are limited typically to the minute to hour range. I think the record for GISAXS is 60 seconds or 10 seconds, something like this, but much longer. So really GISAXS with a two-dimensional image. And we are working at ESS. We have a project at ESS together with Lund University, so KTH Lund and others, where we actually install a GISAXS beamline at ESS. And there we want to go to the second regime, yeah, that we can really measure kinetics with GISAXS on the order of a second.
You mean Saga proposal or something on
Saga, exactly. Yeah.
Okay. Thank you very much for your answers.
You're welcome.
Thank you. And now Igor Sukhenko.
Yeah, thank you very much for your wonderful talk. So my question concerns mostly the magnetron sputtering. I think you mentioned in near to the end of the talk. So yeah, you're using this sputtering to deposit either polymers or the organic materials. And
sorry, no, only metals, not polymers.
Metals on polymers.
I see.
Metals on polymer. Only metals on polymer.
Then I guess my question is no longer valid because it was about how to preserve the structure of the deposited.
Very good question.
Metals,
actually, actually, we did this. We deposited polymeric material. When you sputter polymers, you cannot preserve the structure. I guess you know that you then tell, well, the target is whatever PTFE, and we deposit fragments of PTFE. So you have a polymer-like layer, but not the polymer layer. We did this in the past too, but for us, we want a template, which is our polymer film prefabricated, and then we deposit our metal layer on.
I see.
Yeah, and as a side remark next to it, when you deposit something like fluorinated polymers, then you have to clean your chamber afterwards, and this can be quite tedious. So we no longer do this.
Thank you.
Any more questions? Okay, while maybe someone else will decide to ask one more, but I have a lot of questions. I won't ask them all because too
no
much
problem.
time.
I have time.
Like one important thing that I'm curious about. You mentioned that you on the slide where you were mentioning XPS with aluminum clusters growing on different polymeric substrates. Is it XPS also being done in situ, so it's all in one chamber? So you can do GISAXS and XPS at the same time?
Unfortunately not. So what we do here is we repeat the experiment in the lab of our Kiel collaborators, and they have an identical sputter chamber with an XPS on top. Yeah, so we always prepare several samples of the same polymer film. We measure in situ. We prepare samples for AFM and SEM measurements, and then we go with the freshly prepared polymer film to Kiel and we deposit the metal layer, and then we do the XPS. So it's not directly in situ, it's ex situ in that sense, but it's under the same conditions so that we can really compare it.
Yeah, I see. Yeah, it's absolutely reasonable. I was just wondering, like, it would be it's already impressive, but if you somehow manage to put even XPS there, like, it's hard to imagine the geometry how to make that.
Yes, I would love to do it. I don't know. I'm definitely not an expert in XPS. I would love to do it, but I don't know how one could incorporate this. Yeah, but it would be perfect. I mean, we are doing already in situ. If we go directly back to the beginning, I didn't go much into it. If you look at the image here, yeah, we even have here UV vis set up. This is at least in situ. We can also measure the percolation or the electrical conductivity in situ, not 4-point, but 2-point measurement. So this can be done in situ. We cannot do FTIR in situ. We cannot do XPS in situ, but we can maximum do GISAXS, GBUX, of course. We can do UV vis, and we can do an electrical measurement in situ. And we can also, with other sputter chambers, deposit two metals at the same time or oxidic materials, whatever we need.
Thank you. Very cool. One more question from Nazar in chat. When performing GISAXS under continuous illumination, is there evidence that beam-induced defects or electronic excitations influence interlayer diffusion kinetics? How do you separate beam effects from intrinsic diffusion processes?
Very good question. Yeah. So an X-ray beam induces ions or radicals in a film, and especially polymers are prone to it. You can even break bonds. If you do this, you would see an altered growth. Yeah. Then even with the bare eye, if you look on the polymer film as is, I use the word burn, you would see a black stripe. Yeah. Then your film is already damaged. You could, even if you don't see a black stripe, you can still induce radicals, and then the clusters grow differently. Yeah. Then you would see in the AFM suddenly a region where the clusters are larger. Yeah, and for example, not percolated. In order to avoid this, what we do is we take a series of these images with very short exposure, 0.05 seconds, or even smaller. And what we do then, we look at them as a function of time. And if there is no change in the images, this means the X-ray doesn't induce beam damage. And as soon as you induce beam damage, you see a broadening here. You don't see it in the wide angle scattering pattern. This is already too late when you see it there. You see here a slight broadening when you have radiation damage. And this is for us then the case when we say, okay, we cannot measure more than 0.5 seconds per point. And then we typically measure only 0.1 or 0.2 seconds per point. And the ultimate comparison is, of course, when you make an experiment with X-ray beams and then you repeat the experiment without any X-rays, you take the two samples and you compare them under an SEM or AFM, and we do this regularly and we don't see any difference. So we know that our avoiding of radiation damage really works. But it's a very important question. And typically when you make proposals for scattering, you must write a sentence in there how to avoid radiation damage. Yeah, and this is what we did here. Yeah, if you remember this one here, yeah, you see here, yeah, this is why this is the shadow of the sample. We really move the sample to the beam and distribute the radiation dose, and we stay for each point under the critical limit.
Yeah, thank you for the detailed answer. I think we can now move to the second part of your talk.
Okay, I mean, as it is quite advanced in time, I suggest to make, sorry for that. Yeah, you see, Volodymyr, I followed your advice, more sputter deposition. Yeah.
Yeah. Thank you for that.
You can also have the talk, it's no problem. In the second part here, I maybe focus on the neutron scattering. The first two examples, And then I just show the results. So
The applications, yeah. Good.
yeah. So what we do now, no sputtering, we go to liquid deposition. So basically we start with a tree. We chop a tree and we break it down to the nanoscale. These are the cellulose nanofibrils. You can make paper out of it. These are the fibrils, hundreds of nanometer long, 5 nanometer in diameter. The interesting thing is by chemical methods, we can introduce a surface charge on them. And the surface charge is in micromole per gram because they are carboxylic groups. And the higher this number, the higher the surface charge. Yeah, so the surface charge here is given as micromole per gram. So we take these cellulose nanofibrils, we disperse them in water. And what we want to do is we want to make template fabrication. We want to make large scale devices. And we want to use this nano paper as a functional material. This is to say we must put functional groups in. And all what I have shown you beforehand were small samples, 2 times 2 centimeters. Here we use spray deposition. Yeah, we have a roll-to-roll coater which we can put into the beamline. We can coat up to 50 meters of any foil. Here is the spray cone. Here are the X-rays. We measure in situ the deposition on our samples. We have a microscope. We can even have a UV vis inside. And in spray deposition, you have a dispersion. You push it through the nozzle and you atomize it so that individual droplets occur, and these individual droplets land on a surface, and by this you cover the surface with your desired material. Yeah. When I have politicians, when I have to what to say, when we have politicians here, you know we have the Green Party and the Conservative Party. I always tell them, yeah, with spray deposition, you can coat everything on anything. And then the Green Party always smiles and the Conservative doesn't understand it. Yeah, that's the advantage of spraying. Yeah, you can even coat walls on houses with functional materials. And this is what we do here. And you see here already, yeah, when we do this, this is cellulose nanofibrils, 200 nanometer thickness on a silicon wafer. This is a pure silicon wafer. And this here is the coated silicon wafer, blue color, around 200 nanometer. So it's 10 by 2 centimeters. This is large scale, really large scale, because DFG, German Science Foundation, states that 1 by 1 centimeter squared is large scales, and we are 20 times larger. And this is, as I said, these tiny cellulose nanofibrils in water sprayed on the surface. And this is then how it looks like in an optical microscope and in an AFM. You see here these fibrillar-like structures, you see here voids. And our question was, what do we see actually? So first thing you do is you take a droplet of water and you measure the water contact angle. Yeah? Remember what I said, we can put a surface charge on these fibrils. Yeah, bacterial cellulose here in blue is basically without surface charge. And you see when we spray it, we get a rather high roughness, 20 nanometer. When we use charged cellulose with carboxylic groups, you see that we can reduce the surface roughness down to 2.5 nanometer. And at the same time, the water contact angle first follows the roughness and then increases again. Why? First of all, we have the cellulose nanofibrils. When you charge them, the film stratifies. When the film stratifies, the roughness goes down. When you put a water droplet on with increasing surface charge, the water droplet is more and more repelled. First, it follows the roughness and then it is repelled. So this explains this graph. And you see here that we have a sweet spot around 1000 micromole per gram surface charge of the cellulose nanofibrils, where the water contact angle is low, and we can expect a good inhibition if we use water-based materials. And the first question is, where's the water going? Yeah, I mean, everyone can do it in the morning. You take coffee and you let it drop on your napkin, and you see how the coffee and the water imbibes into this napkin. This is the water uptake. And actually this graph here shows that even with X-rays, we can detect water. Remember what I said about the Yoneda peak. This Yoneda peak occurs at the critical angle of the material. The critical angle is proportional to the square root of the density. And this is this vertical cut from the GISAXS images. And you see here, this is the critical angle of CNF. And we see here something else. This cannot be the silicon substrate. The silicon substrate would show up here. This is water. So we can detect with X-rays water. And we could calculate the water content between 4 and 16% in our cellulose nanofibril layer. So this was actually the first time we could detect water. And secondly, we confirm this is measured under dried atmosphere. You can never dry cellulose. There's always water in cellulose. Good. And this was the basis. So when you talk about water uptake, you talk about neutron scattering. You can easily trace deuterated water in structure. And this is what we did. We put actually a humidity chamber. We brought it to Munich, to the KWS3 GISAXS beamline, and we made a GISAXS experiment during humidification. And this was actually very important because if you look here, you see a fibrillar structure and you see voids. Okay. If you look with GISAXS, it's very interesting. You find actually 3 structures, a smallest structure, around 6 nanometer in diameter. These are the CNFs. You find a second structure around 16 nanometer. These can be bundles. And then you find a third structure, which is on the order of 50 nanometer in diameter. What is this? When you look at the water uptake, relative humidity 90%, this large structure has a spherical appearance. So you have D2O and you have a spherical appearance. So this is a water droplet. This means in my cellulose nanostructure, I have water droplets. Where can they occur? In the voids. So we detect here spherical voids in our cellulose nanofibril template. And now remember what I said. We want to imbibe a functional material into exactly these voids. So you can use a water-based material to imbibe this into this cellulose nanofibril structure. And this is actually what we then did. We used here P.PSS. This can be used as hole blocking layer in solar cells. What we did actually here, we sprayed cellulose nanofibrils and we sprayed the P.PSS. And then we looked at the hybrid structure. You can do this in the lab. P.PSS is semiconducting. In the lab, you can do 100 humidity cycles, up 95%, down 5%, and so on. And I want to take a look with you first here at the blue lines. Here you see here the first cycle 5%. We have a high conductivity, then we increase humidity, the conductivity goes down. Then we reduce relative humidity, conductivity goes up. Then we increase humidity, goes down, decrease, up, and so on. You can do it 100 times. The question is, what is happening on the nanoscale? Can we explain this on the nanoscale? And we use GISAXS for this. And of course, as you said, we cannot do 100 cycles at the reactor with GISAXS and humidity cycle. So we focused on the first 2 cycles. And this is actually what comes out. This is our structural analysis. We know the structure of our CNF template is individual fibrils bundled into agglomerates and voids. And the voids are filled when we imbibe the P.PSS in water with this solvent, the solvent water with the solution, the solvent evaporates, and the P.PSS is left as spherical aggregates. And it also coats the CNF. This is known via AFM measurements from a group in Linköping University close to Stockholm. So we start with this drying. Then we humidify. We see that from our GISAXS analysis, these particles become larger. we have a de-wetting on the surface of the CNF. In the first wetting cycle, this was the first wetting cycle. We have here a growing of these structures and a de-wetting and a slight reorientation of the CNF. Then we dry it. We have a reorientation. We have here a conductive path of P dot PSS on the CNF, and these structures here slightly grow in size again, especially compared to the beginning. And this cycle here, 2 and 3, we wet again, these structures become smaller, de-wetting, we dry again, we have again wetting, and structures larger, correlates perfectly with what we see here with the cyclic humidity changes. So we can explain here macroscopic phenomena, the conductivity, with nanoscale changes. And even more important, what we did not know at that time, when you take these P dot PSS CNF films and you swell them, you humidify them, they do not swell. So we measured here with XRR the size, the vertical size of our hybrid films, and they stay the same. If we would use pure P dot PSS, it would swell. So what we have here is that we don't observe swelling, but this CNF is like a structural network. It can slightly rearrange, but it doesn't swell. And this is very important. This gives you a stability of your electrode. You see here, important is you can, when we go out here, we always have humidity. But the humidity changes, of course, the conductivity, but we can do this 100 times. We can dry it and humidify it, and the structure changes in a cyclic way and does this in a stable way. And this is very important, what we got to know from here. And we can then go just as a next step, a step further. We can really then take our P dot PSS on a silver nanowire electrode. Yeah, this is basically the half cell of an solar cell. And then we put, we spray deposit EPA, DMSO, and methanol as typically used solvents. You see here the roll-to-roll coater, which we really then did in situ with GISAXS. And we can follow the different crystalline changes here. And especially then we can look what happens in this P dot PSS when we see that its nanostructure changes. Yeah, this is the crystallite size change as a function of spray time and deposited volume. We can correlate this again with the sheet resistance and with the optical transparency. And with this, actually coming back to my first slide of sustainability, we can avoid nasty solvents but use methanol as the best compromise in terms of conductivity and transmission. Just to finish my talk, as a very nice example here, how to spray an electrode layer. What you can do is you can use silver nanowires. You can spray them on your paper, or you mix with cellulose and nanofibrils and you spray the mixture. And always my question is, it's somehow counterintuitive. When I add an insulator to a metallic mesh, it should become less conductive. And if you look, however, I just go through here. You see here this type 2 electrode. This is the mixed cellulose silver nanowire electrode. It has a lower transmittance as the pure silver nanowire electrode or silver nanowires on top CNF, but it has a much lower sheet resistance. And the question was, why? And actually you have a combined effect of the solvent evaporation and of the hygroscopic properties of cellulose. They attract the water, and by this they cold weld the silver nanowires. And if you cold weld silver nanowires, they become more conductive. If you just spray silver nanowires on top of CNF, the water is driven away by the CNF layer, and the silver nanowires just lay on top. This is what we see also in the GISAXS. There's not much changing, just we see more material, while we see a nanostructure formation when we spray the mixture. And this nanostructure formation are these junctions, these points here, which we see as nanostructures in our GISAXS signal. So we can even explain here why we can make very good electrodes by mixing CNF and silver nanowires. And you see here they are really stable. these layers, yeah, we spray them here on PET. On the right side, you see an electrode, yeah. Here the electrode shines nicely. And on the left side, if you look, you see here an LED. Yeah, my student Marie Betka, she's now postdoc in Tokyo. Yeah, she takes this silver nanowire layer and she tortures it quite heavily, and you still that it's really stable. Yeah, you see that the LED is still shining. Yeah, so again, confirming that whenever you add cellulose, you can really create stable networks under the action of cellulose. And just to finalize, we use then all our knowledge. We can make capacitors out of it. We can make LEDs out of it. We can make novel substrates out of it. And then we can even make here a prototype sunblind and really spray coat solar cells with a moderate efficiency, but they are sprayed and use indeed silver nanowires and cellulose. With this, I would like to finish. I think I've walked you in a, I agree, demanding talk through sputter deposition for functionalizing materials. We can really look into diffusion layers, and we can combine our knowledge and our analysis with GISAXS to really make a real solar cell out of it. And I want to thank my group in Stockholm and here in Hamburg, and the funding agencies and my collaboration partners. And of course, you, a big thank you for your attention.
Thank you very much, Stephan, for the wonderful talk with a lot of interesting details. So, questions from the audience? I can perhaps start. Essentially, you're using cellulose as a sponge of sorts, right?
You could say like this. It's more than, yeah, it's a stable sponge. Yes.
So you used it in the combination with silver nanowires for the applications you just described.
Yeah.
Did you try other materials? Maybe some. I don't have any exact idea yet, but if it's like obviously it works nice with water, it works nice with this application as well, but maybe there can be some other interesting applications for this.
Yeah, so first of all, we want to go away from silver. Yeah, the problem with silver is the semiconductor industry is using it quite heavily, and they are using the majority of the silver stock.
Yeah.
So what we actually want to do is go to copper, and you can create copper nanowires in alcohol. This is also mixable with cellulose. Yeah, you can mix ethanol with water, and so cellulose with the silver nanowires or copper nanowires. We are also, as I showed here, using other materials. Yeah, we use P.PSS, which is a hole blocking layer in solar cells, which are added into the cellulose nanosponge. We can even put it into an active layer with the P3HT PCBM, so semiconducting polymer plus buckyballs we can add in, and then you have a very stable substrate for solar cells. We are currently investigating, this I did only very briefly here, we are currently investigating what's the influence of typical solvents like chlorobenzene and chloroform on the cellulose mesh. Yeah, basically we asked the question: does the cellulose mesh still retain its properties when we use chlorobenzene, chloroform, and so on as a solvent? So we are quite flexible. Yeah, basically what you can do is you have your cellulose substrate and you can put anything on you want, and it goes into this nanovoids, and by this it partially encapsulates even what is inside, and by this you are very free. You don't need to premix it. You can make a real layer by layer coating, and by this you can create your functional material.
And thank you. And what is the minimal thickness of such a layer that you can still have while functional? I mean, obviously you
Yeah.
can make it like
Between 20
1,
and
2
100
nanometers.
nanometer. Yeah.
Uh-huh.
It depends a little bit on the material used and on the solvent. It can be as low as 20 nanometer or as high as 100 nanometer. Yeah. In that range, you can have functional substrates. What we show here, they are thicker. Yeah. For example, this here is a 1 micron or 2 micron thick layer of cellulose. This is with P.PSS. We can have freestanding films of 2 micrometer. Freestanding conductive cellulose films of 2 micrometer thickness, 10 centimeter long, 2 centimeters wide.
Yeah, that is a very big sample.
Yeah. Yeah, this is very big, but in the end, we need this because we want to use this as solar cells, and solar
Yeah.
cells have square meters. And
Yeah, of
as I
course.
said, it depends. If you want a cluster layer with, say, gold or silver clusters, I didn't show this, then you can have a nominal thickness if you calculate the effective thickness of 1 or 2 nanometers. So you have very well dispersed metal clusters on a surface. Yeah? It depends on the functionality. If you want an electrode, we think here that 100 to 200 nanometers is sufficient if you have it on a substrate.
Yeah. Thank you. If there are no questions, I can actually maybe return to the first part and ask some of the questions that I had.
Sure.
I think it was slide 21 about silver clusters. I didn't write the question, but I wanted to ask something there.
Yeah. Just give me a second.
Yeah, of course.
Too many animations.
Probably
Here.
slide 20. Oh, yeah, this slide 20 then. Okay. I had it noted, but someone else already asked it. I wanted to ask about like how you actually distinguish clusters that in terms of that like morphologically you see that they are different, but if they touch, they essentially start acting as a one. But that was already discussed. Yeah.
Yeah. So if you look also here, when you have clusters, you see this line here. It's a line. When they start touching each other and you approach the percolation, this here becomes like a triangle. Yeah, you see it here also in the simulations.
Yeah.
And this is an indication of a percolated layer. Yeah, if you would look at the intensity here, the intensity is in this line concentrated, and here the intensity shifts upwards. Yeah, this has to do with the Yoneda peak. Then you see a layer of a higher density. Yeah, this is basically the silicon Yoneda peak, and then this is the silver Yoneda peak. So you see a rough layer of silver. Yeah, a full layer with a roughness. This is here the shifting of the intensity. Yeah, so this is, as I say, it's very powerful. Even without telling me, I made this. We made this, that we were deliberately not told, and I tell industry always, if you tell us, it's faster, but we can by this derive the material inside, and we can tell you really when the clusters make a percolated layer. And in addition to this shifting here, we can calculate this 2R/D ratio. When this is 1, the clusters touch each other. So this, we have several methods to verify the percolation. And just as I mentioned, if you make an experiment and you basically decide you want only to follow this peak, this is fully sufficient. When you want to know the distance, already from the distance, you can, under some assumptions, deduce electrical properties. So the depth of information depends on the depth of analysis and of how much time you want to incorporate. And this comes back to the machine learning. Basically, what we did here is we simulate and make an eye-by-eye comparison. You can ask the students how many images they can compare per day. Certainly not 50,000. And this is why we use the machine learning to compare these key scattering features with our experimental data and then deduce after training. We know this is hemispherical with this distance and radius. We deduce the actual nanostructure in an automated way.
Yeah, yeah. That's a perfect application for machine learning.
Yeah.
One more very small question. Slide 28. About gold. 27 then. Yeah. You can measure it essentially by GISAXS, how deep
Yes.
the gold is going. How do you confirm it? Well, do you just take the sample out and measure with so not in situ, right? And with which methods?
So we did XRR on this, and we find also this enrichment layer.
Okay.
Yeah. So we have XRR, and the other one with when you do TEM and side cut TEM, it's very difficult to find this. So we relied here on our knowledge of the XRR and on the GISAXS. And of course, this is not, there's a little bit more behind. Yeah, when you see this, this here, yeah, you see here oscillations in these oscillations here, they have nothing to do with physics. We are just measuring so fast when our shutter in the sputter chamber opens, this induces vibrations and the sample vibrates, and we see this as sample vibration, and we calculate back the actual incidence angle, we correct for this, and then we can we see here these fringes, yeah, which encode polystyrene thickness and density, polystyrene layer thickness and density, and we do actually simulations. So we simulate the scattering patterns one by one, and then we simulate these maps. I have not shown this, and then you can unambiguously deduce from the simulation what is happening. You could argue that the gold goes fully into this film of 100 nanometers or 80 nanometers. You could say it stays only on top. You could assume a swelling of the film. We can all exclude this via the simulations, and therefore, using this formula, as I said, we follow the film, the remaining polystyrene layer thickness and the loading. And we, as I said, we know the XRR, so we don't need to cut our sample. Yeah, and I'm not sure how you would measure such a small loading with electron microscopy. Yeah. We don't think they are clusters. We have, from what we see as a growth mode or diffusion mode, it should be individual gold atoms which diffuse in.
Yeah, if it's 5 nanometers, it's essentially like 2 layers.
Yeah.
Or one, depending on material.
Yeah, but with a very, very low loading. Yeah, this is
okay, I see that there are no other questions. Then I think we can finish. As you see, I've told you that it will probably take about 2 hours. So we are perfectly fine on timing. Everything was well. I think thank you very much again for giving this lecture. It was very interesting, and yeah, hope to see you again.
Yeah,
maybe
I do hope so.
Even live here at the better times.
Yeah, I wish you, first of all, I wish you all the best, and I cannot say much except that I hope everything, and once I hope you defeated the Russians, and when there's no war anymore, we will meet in Kiev.
Yeah, thank you.
I will come, Volodymyr.
Yeah,
I promise you.
Let's hope for that, and thank you once again.
Otherwise, you are also very welcome here in Hamburg, also for joint projects at the Synchrotron or at KTH, or at international conferences, like maybe soon.
Yeah, maybe next track, actually.
Yeah, super. So I wish you all the best. Yeah, I cannot say much. Keep heads up.
Yeah, thank you.
And
Thank you once again for the lecture and
Yeah.
for coming.
thank you very much. And
Goodbye.
yeah, bye.
Thanks, Stefan. Bye. Thanks, Vladimir. Bye.
Thank you.